Welcome back to another explainer. Imagine, just for a second, that you're the lead architect of this massive, futuristic global metropolis. You've laid out all the roads, you've connected the neighborhoods, and people are moving in way faster than you can build. But then, out of nowhere, you realize you've completely run out of house numbers. No new numbers means no new houses, no new businesses, and absolutely no new growth. It sounds kind of like science fiction, right? But this is the exact reality our internet architecture actually faced. Today, we're unpacking the massive mathematical crisis of how our digital world literally almost ran out of room, and the epic infrastructure upgrade that saved it. Here is our roadmap for today's explainer. We'll start with the rules of the web, then look at common network protocols, understand IP addresses, dive into the IPv4 exhaustion problem, and finally see how IPv6 comes to the rescue.
All right, let's jump right into section 1, the rules of the web.
So what exactly is a network protocol? Basically, it's a set of software rules that computers follow to send, receive, and interpret information. Think of it like a spoken language. If one computer speaks French and another speaks Japanese, they're not going to get very far without a shared set of grammatical rules and vocabulary. Protocols are that shared language. Oh, and fun fact from our source material, NCP, or Network Control Protocol, was actually the very first one of these rulebooks ever established. Moving right along to Section 2, Common Network Protocols. Different tasks need different rules, right? So let's rhythmically bounce through this list as a quick refresher. TCP/IP is your foundational internet rulebook. HTTP is what your browser uses to handle HTML documents on the web. Tack an S onto that for HTTPS, and boom, you've got a secure connection that actively protects your data from hackers. Then there's DHCP, honestly, the unsung hero here. It automatically assigns IP addresses so your phone can magically hop onto a coffee shop's Wi-Fi without you doing a thing. Finally, we've got SMTP for firing off your emails, and FTP for when you need to transmit files directly. Pretty straightforward.
That brings us to Section 3, Understanding IP addresses. Now, we've all heard the term, but let's take a second to really appreciate the sheer scale of its function in the digital metropolis we've built. What actually is an IP address?
At its core, the Internet Protocol, or IP, guarantees that every single device gets a totally unique identity. This is absolutely crucial because it ensures that when you request data, it routes directly back to your specific screen and not, your neighbor's. Whether we're talking about version 4 or version 6, this protocol is the singular backbone of global data routing.
Which leads us to the drama in Section 4, the IPv4 exhaustion problem.
For the longest time, the internet relied on IPv4. This is a 32-bit address system expressed in dotted decimal notation. You've definitely seen this before. It's those 4 numbers separated by periods, typically looking something like 192.168.1.1, sitting right there on your home router. It was simple, it was elegant, and it was the foundational standard that built the web. But there was a massive catch. Because it's a 32-bit system, it can only generate about 4.3 billion unique addresses. Now, back when the internet was mostly just a few research computers, 4.3 billion felt like an endlessly vast number. But then everyone got a smartphone. Smart TVs became a thing. Suddenly, even our refrigerators needed an internet connection. The math caught up with us, and we hit a terrifying truth. We were experiencing total address exhaustion. We literally ran out of room. So how did the entire internet not just crash and burn? Well, the tech community rolled out a temporary fix using Network Address Translation, or NAT, along with private IP ranges. Honestly, you can think of NAT as the digital duct tape deployed to hold the world's infrastructure together. It allowed multiple devices in your house to share just one single public IP address. It artificially conserved the numbers and bought us the crucial time we needed to figure out a permanent fix. And that brings us to the hero of our story in Section 5, IPv6 to the rescue. When the developers built the 6th version of the Internet Protocol, they weren't messing around. They didn't just want to add a few million extra addresses. They wanted an upgrade so vast we would never face exhaustion again. They created an address space of 3.4 times 10 to the 38th power. That is 340 undecillion unique addresses. It's a completely mind-bending scale. How did they pull this off? By swapping that old 32-bit system for a massive 128-bit architecture. And because the numbers are so unimaginably huge now, they couldn't stick with the old decimal format. So IPv6 uses hexadecimal notation. Yeah, it looks far more complex, with 8 groups of 4 characters separated by colons, but the mathematical real estate it unlocks is practically infinite.
Let's put them side by side, because IPv6 completely revamps how networks behave. Check out the configuration row. While IPv4 needed a lot of manual setup or DHCP, IPv6 is incredibly self-sufficient, with stateless auto-configuration and renumbering. Then look at integrity. With IPv4, true end-to-end integrity was basically impossible because of that NAT digital duct tape we talked about earlier. But with IPv6, every device gets its own public address, making direct end-to-end connection integrity fully achievable. Even better, IPv6 bakes in encryption and security features right out of the box, something IPv4 totally lacked inherently. And finally, the header, the metadata attached to your digital envelopes. IPv4 headers were kind of clunky, fluctuating between 20 and 60 bytes. IPv6 streamlines that into a highly efficient, fixed 40-byte header. It's just a vastly superior system.
Now, with all these amazing features, especially the built-in security and vital support for multicast communication, you're probably wondering, why aren't we completely on IPv6 right now? Well, upgrading the entire planet's infrastructure is a massive undertaking. The transition has definitely been slower than anticipated, but adoption is steadily, gradually gaining traction. It is absolutely necessary as the internet stretches to support the explosive, ever-growing number of connected devices we rely on today. So the crisis was averted. We upgraded from a pool of a few billion to a staggering 340 undecillion options. To put that into perspective, it's often said that IPv6 has enough unique IP addresses to assign one to literally every single atom on the surface of the Earth. Let that sink in. So the question I want to leave you pondering today is this. Now that we have basically zero limitations on our digital real estate, what are we going to choose to connect to the internet next? Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.